Hi there, in this video we're going to continue our derivation of the least squared estimators in matrix form. At the end of the last video we found that we were able to write out our sum of residuals squared in this particular form up here, where this first term here is in fact our vector of our residuals transposed, and this second term here was our vector of our residuals. Okay, so how do we actually simplify this thing a bit? Well, the idea is that we can actually write this out a bit more simply just by applying the transpose operator first of all to this first parenthesis. The transpose operator is a linear operator, so I can just apply it to each bit in turn. So I just get y transpose minus, it's actually going to be beta transpose or beta hat transpose times x transpose, because when you apply the transpose operator to a product of matrices, then the order of multiplication inverts. And then we just got our original second parenthesis, which is just y minus x beta hat. Okay, and then we can just simplify this by multiplying out these two parentheses. I get, for my first term, I actually just get y primed times y, where y primed is y transposed. The second term, I get y transposed times x times beta hat. And then the third term, I get a beta hat transpose times x transpose times y. And then for the final term, I just get beta hat transpose times x transpose times x times beta hat. Okay, so I've got out something, or my sort of form of my sum of square residuals, and it's quite messy. How do we actually go ahead dealing with this thing? Well, let's just remind ourselves of what we're actually trying to do. What we're trying to do is we're trying to minimize this sum of square residuals over our choice of our parameter vector beta hat. And we're differentiating s with respect to beta hat rather than just, let's say, an individual beta. Why are we differentiating with respect to a vector? Well, it's because we have got essentially p choices for our parameter vector, because our parameter vector beta hat is in sort of its individual form, it's sort of got beta 1 hat through to beta p hat. So we're going to have, in fact, p first order conditions. And that makes sense, right, from what we found when we were just considering the bivariate model, where we just had y being equal to alpha plus beta xi. Here, when we were choosing alpha and beta, because we had two parameters in that model, we actually had two first order conditions. So when we have p parameters in a model, that kind of makes sense that we're going to have p first order conditions. So the idea is that we're trying to differentiate our s with respect to our parameter vector beta hat. Okay, it looks quite tricky, but in fact, we've covered everything we need to be able to do this. The first term's easy enough because this first term here, y prime times y, doesn't involve beta hat, so that just contributes nothing. So that just kind of disappears when I differentiate with respect to beta hat. I'm actually going to forget about the second term for the time being, and I'm just going to cover the third term because it's a bit simpler to deal with. This actually, as it turns out, is exactly of the same form as our sort of x primed times a. Because when we think about the dimensions of these things, this sort of beta primed here is going to be a 1 by p vector, x primed is going to be a p by n matrix, and y is going to be an n by 1 column vector. So this is just some sort of row vector, 1 by p row vector, times something which is going to have dimensions p by 1. So what I get out in the end is these sort of two p's cancel with one another, and I just get a 1 by 1 thing out at the end. So I've actually just got a scalar quantity here. And because I can sort of think about all of my terms have to have the same dimension, each of these terms itself is going to be scalar, right? Okay, so because we've got a scalar quantity, we can appeal exactly to what we had before when we were differentiating x primed a with respect to x. We said that when we differentiate x primed a with respect to x, we just got out a. Although in this case, we're differentiating with respect to beta hat. So what does this sort of third term contribute? Well, it contributes our x primed times y, because we differentiated with respect to beta hat. So it's got to have out the same dimensions as beta hat, In other words, it's got to be a p by 1 vector, which is exactly what x primed times y is. Okay, now that we've done this term, oh, in fact I should sort of have a minus there because I've got a minus at the front of it. Now that we've covered this term, we can think about what this second term contributes. Well, this second term is just this third term all transposed. You can see that because if I was to transpose this, then the beta hat would go out the front, but it would be transposed, and then I'd get an x transpose, and then finally I'd get a y transpose, which is just y itself. So in fact, this second term is just the third term transposed, but we've already proved that the second term is actually a scalar term, so these two terms are actually exactly equivalent because for a scalar quantity, the transpose of that scalar quantity is just itself. So this second term actually is going to contribute exactly the same, it's just going to contribute x primed times y. Okay, so now we're finally left with this sort of most complicated term which we have here on the right, but actually it's probably the simplest to deal with in some ways because this is already in quadratic form, except our matrix A is just x primed x. So you can sort of think about this beta hat primed as being equivalent to our sort of x primed in our original notation, or which we showed in the previous video, and then we've just got beta hat just being the x on the end. And I've just realised that this final term here should actually be plus because of the fact we've got a sort of minus times a minus in both parentheses. So what does this final term contribute? Well, we sort of found when we differentiate this quadratic form here that we just got out 2 times our matrix A times our x. But in this case, our matrix A is in fact x primed times x, and sort of confusingly, our x in this notation is in fact beta hat. So we just get out a sort of plus 2x primed x times beta hat. And we know that this whole thing has to be equal to 0 because we're minimizing the sum of the square errors. So when I differentiate it, that differential has to be equal to 0. But it's not just equal to 0, it's actually in fact equal to a vector of zeros where the vector has p components because in fact we're going to have p first order conditions because we're going to have a first order condition for each of our sort of beta hats in our beta hat vector. In the next video, we are going to finalise our derivation of the least squared estimators in matrix form. I'll see you then.